Oh, now I got autofocus working. Okay, here we go. This is the test point I'm working on right here. This resistor right there. On the SAMs it shows it down here somewhere. I think it shows it right down in here. I'll show you where it shows it on the SAMs. They show it, this resistor right here, right at this junction, which is the same spot. So if you want to clip there, that's fine. I clipped right here because it was the same place and was easier to get to. This capacitor, by the way, is a C15. That's the one that softens or takes the AGC pulses and turns it into an AGC DC voltage. Just a quick note on that. Let's just talk about that for a minute. Let's make this a little smaller. Let's talk about what's going on there. AGC. Okay. What's going on is this uses what they call keyed AGC, which means it actually looks and samples the signal level only during the retrace period. That avoids noise and such from getting in there and causing AGC to think it's a strong signal. I think they did a lot of that had to do with airplanes flying overhead and causing strangeness that was screwing up less sophisticated AGCs. But the bottom line is what you're looking at here is a pulse from the flyback comes through a capacitor to the plate of this tube. There's a capacitor right there. I think that's a disc cap that's down on the flyback. So you get this 680 volt pulse, and you have a tube that's essentially turned on or turned off based on the strength of the video signal. So if you have a strong video signal going in there, you'd end up turning the tube off, or turning the tube on, and that conducts that causes the tube to conduct, and it weakens this pulse. It drags this down. Just like if you check the plate voltage of a tube that had no signal on it, it would be high. When you apply a signal to it, the tube begins to conduct. The voltage, the plate drops down. It's basically how it amplifies. It has that varying plate voltage based on what's going on in the grid. Well, this is doing the same thing. It drags the plate voltage down when it conducts strong signal. If there's no strong signal, it stays high. Now that strong signal is going to be the sync signal that correlates to this pulse. So in other words, during this downtime, it's not even looking because essentially the tube has no plate voltage. Plate voltage turns on for just a fraction of a second, samples the sync pulse, which happens at the same time. If your horizontal is locked, that's key. You gotta have a horizontal lock, otherwise none of this really works. Anyway, if the horizontal is locked in and working properly, then it says, "Oh, I've got a strong horizontal signal, a strong horizontal sync signal, so I don't need much AGC." Or I have a weak horizontal signal. Tube doesn't turn on, voltage stays high. This comes up, goes through here, and ends up. Let me get over here. Ends up going through this network, being filtered. There's a voltage dividing network happening here, and a filter here. There's a filter. There's a filter on the RF side, and there's another filter. This guy right here. These are filter caps, just like regular old power supply filter caps. They're not very high. They're not extremely large values because you got a fairly high frequency. Remember, this is taking place at 15,000 times a second, so it doesn't need a huge high voltage, high value cap like on a regular 60 hertz power supply. Anyway, that's the junction you're trying to check on and see if this is varying up and down. And you should notice that it'll go up and down based on the signal strength that's there. So you clip on here and you look at that signal and see where you are, and with the signal, and you shouldn't see any hash coming through. That would indicate that this thing is sampling properly and it's filtering out this big pulse, because what's actually coming through this line right here, through the plate line, is this, but with varying amplitudes. When it goes through this filtering network, it gets turned into straight DC that's added or subtracted from what's there already to influence the gain of the amplifiers. Anyway, I just wanted to clarify a little bit on that. Go on autofocus. Well, now it won't get. Anyway, test point 1 is where you want to go. Alright, I've got this hooked up to a test point. The SAM's a little confusing. You really need to kind of take a look and make sure you're connecting this to it. Basically, it goes on the one side of this cap, which I believe is C15, and that resistor, which I'm not sure which one it is, but if you look at the SAMs, you'll see where I've connected up to. And what I'm doing is I'm looking at the AGC, the Keyed AGC, to make sure it looks nice and clean. And here it is. That's AC, so we're not seeing the truth. You're seeing there's basically no hash or anything going on there. It looks very clean, and I'm at about negative. Let's see, 1, 2, 3, about 3.5, and that correlates. It's funny, you see this noise on the screen, but it's not. I don't see it. Let me turn the intensity down. It's about -4.5, which is confirmed by what the multimeter says. But the problem with the multimeter is it could show a negative voltage, but you wouldn't see any horizontal hash if it was there. And I'm cranking this thing way up. Let's see here. And there's still nothing there really significant to look at. So when you're checking AGC voltages that are coming out of a Keyed AGC, it's very important to use a scope to look at it, because if you don't, you can end up seeing negative voltage, which is fine, but that's because your meter is giving you the average and not showing the hash. So anyway, I'll get a little closer so you can see where I got it hooked up to. I'm hooked up right to the bottom of a 1500 ohm resistor and the other side of that cap, which was C15. That's the correct test point that you should be looking at for a AGC voltage. Anyway, I think that pretty much covers the sync situation here. I can't think of anything else I need to address. So anyway, there you go.